Water is heavy, fast, and unforgiving. A rushing river represented a hard stop to expansion, a churning wall trapping tribes on a single bank. To cross that barrier, they faced a brutal reality of physics. Human bodies are dense, and without constant, exhausting physical effort, we sink. Observation eventually changed that. Fallen trees and drifting branches stayed on the surface, moving with the current rather than disappearing beneath it. Gravity applies a downward pull, pressing the wood deep into the river. But water fights back. This is buoyancy, an upward lifting force directly opposing the weight. Because wood is less dense, upward forces win the tug-of-war, keeping the log afloat. Stepping onto that floating timber was the moment we stopped simply staring at the shoreline. We started using the physical properties of the planet to bypass our own physical limitations. A single cylindrical log rolls. Balancing your weight on one is difficult, and steering it across a strong current is almost impossible. To fix the roll, early innovators lashed multiple logs side by side. This created a wide, flat platform that resisted tipping. In places where thick timber was scarce, like the marshlands of the Nile Delta, people grabbed what was nearby. They took large bundles of hollow papyrus reeds and bound them extremely tight, trapping air inside to maximize their buoyancy. These rafts and reed bundles worked, but they sat low in the water. They were heavy, soaked up moisture, and created massive drag as they sluggishly pushed against currents. To move faster and stay drier, shipwrights stopped tying pieces together and started subtracting material. They took a single massive tree trunk and carved out the center. This required intense labor. Using primitive tools like this stone adze, combined with small, controlled fires set along the middle of the log, builders slowly chipped away the charred heartwood. Here is the first true hull. This watertight shell pushes the waterline outward, creating a dry space. By removing dense wood, the streamlined shape parts the water cleanly, slipping past the fluid with very little resistance. By designing a hollow structure, early humans solved the drag problem, and so they engineered a way to stay dry and move rapidly, instantly expanding their hunting and exploring range. Even with a sleek hull, propulsion relied on muscle. Paddling a canoe meant you could only travel as far as your own arms and calories would allow. Around 4000 BC, mariners looked up. They placed a vertical mast in the center of their boats and hoisted a woven cloth. This illustration shows the mechanics of the first square sail. A rectangular piece of fabric tied to a horizontal beam physically catches invisible air currents moving from behind. The trapped air generates a massive forward thrust vector, doing the work of dozens of rowers. Now, a heavily laden cargo vessel could push steadily upstream, completely overriding the resistance of the river current. Breaking the physical limits of human stamina shrunk the map. River journeys that required weeks of brutal rowing were completed in days, allowing distant settlements to exchange goods and lay the groundwork for vast trading networks. With hulls reducing drag and sails providing infinite energy, boats grew larger and highly specialized to their local environments. The ancient Egyptians needed to transport towering piles of grain and huge multi-ton limestone blocks from quarries to construction sites. They turned the Nile into a massive supply route. Local marshwood couldn't support that kind of weight. So they imported towering cedar logs from Lebanon to build enormous transport fleets. They meticulously fitted these cedar planks edge to edge, tying them tight with ropes rather than using iron nails, creating massive 140-foot solar barges. Over in Mesopotamia, the Tigris River was too fast and chaotic for rigid barges. Locals engineered heavy wooden rafts called keleks that stayed afloat using dozens of inflated animal skins acting as massive air pockets. These enormous, locally adapted vessels moved grain, armies, and architecture. Mastering heavy water transport was a strict prerequisite for maintaining the world's first cities. Today, our global supply chain relies on sprawling steel container ships moving thousands of tons of cargo across oceans. The materials have changed from stitched cedar to welded iron, but the structural demands have not. A massive modern hull must still flex and hold together under the extreme stretching and twisting forces of the sea. Modern naval architects use advanced software to calculate the exact same principles of displacement and stability that a Bronze Age shipwright felt intuitively in their hands. When a massive steel bow crashes through heavy ocean waves, it relies on thousands of years of accumulated engineering to part the water and stay afloat. By studying the physical limits of buoyancy and wind, early builders turned an impassable water barrier into a worldwide highway system. The modern globalized world can be traced back to a single hollowed-out log.